For today's Colloquium, we have the pleasure of welcoming Claude Lebrun from Stony Brook University, who is going to tell us about mass, scalar curvature, Kaehler geometry, and all that.
Well, thank you very much. It's a pleasure to be here. The work I'll be talking about today is joint with Hayo Hein, who's at Fordham these days, although he was still at Maryland when we started the project. And our paper, which is called Mass and Kaehler Geometry, is in Communications and Mathematical Physics. It was recently. I don't want, so this is intended for a broad mathematical audience, so I'd like to just begin by reminding you about some of the basic concepts in Riemannian geometry. So a Riemannian metric is a positive definite inner product on the tangent space of a manifold that varies in a smooth way as you go from point to point. And when you have, that allows you to measure the length of the tangent vector, and by integration, therefore, you can measure, well, the speed of a curve. Integrated gives you the length of the curve. So there's a notion of length. It turns out, though, there are actually curves called geodesics, which are locally the shortest possible curves in the manifold. And there's a map from the tangent space, or in general, it might only be defined near the origin of the tangent space, mapping the tangent space to the manifold by taking a tangent vector to the endpoint of a geodesic of the same length, which leaves the point with that initial velocity. So you go in the direction of the vector for a distance equal to the length of the vector, following the shortest path possible. And this actually is a diffeomorphism from a neighborhood of the origin in the tangent space to a neighborhood of the point in the manifold. So it's not just that, a manifold is something that locally looks like Euclidean space, but actually there's a standard way of comparing the tangent space, which is really just a copy of Euclidean space, with the manifold by using this map. And the degree to which this map is not an isometry, to which the degree to which it distorts distance is sort of an intrinsic measure of whether the manifold is curved or flat, meaning locally looking like Euclidean space. So one of the nice little lemmas that one proves in a differential geometry course is that actually under this map, so there's a notion of distance in a Riemannian manifold. Given 2 points, the distance between them is by definition the infimum of the lengths of all curves between them. And under this map, actually, if you take a small, say, epsilon radius ball in the tangent space, it goes exactly to the epsilon ball with respect to this notion of distance in the manifold. So one interesting invariant of a Riemannian metric is this scalar curvature, which is a function on the manifold that takes values in the real numbers. This is sort of the easiest, most intuitive kind of curvature to understand. What it does is it compares the volume of a small ball to the answer that you would get in Euclidean space. But I've just told you, of course, the image of a small distance ball is exactly the image of a ball in the tangent space under this exponential map. So this is pretty computable. And it turns out that if you take the volume, so there's also a notion of volume in the Riemannian manifold, the volume of an epsilon ball divided by what the Euclidean answer, which would be the radius to the dimension times a universal constant depending upon the dimension. To lowest order it looks like 1, and then there's a quadratic deviation, and the coefficient is essentially the scalar curvature. For historical reasons, that we don't take this coefficient to be the scalar curvature, but rather it's minus the scalar curvature over 6 times the dimension plus 2. And then and then next there would be something of order of the radius of the ball to the 4th power. So we say that a Riemannian manifold is scalar flat if its scalar curvature is identically 0. So for example, Euclidean space is scalar flat, but the point is that when you say a manifold is flat, you're saying that it looks like Euclidean space, Scalar flat is a very weak condition compared to saying the manifold is flat. It's true of flat manifolds, but most scalar flat manifolds are not flat in the stronger sense. So there's so the scalar curvature is kind of an easy, intuitive thing, but it actually contains it's not a very strong invariant, and it doesn't control the geometry very well. If you wanted a little more control, you could look instead at the Ricci curvature. The Ricci curvature is a function on the unit tangent vectors. Given any tangent vector of unit length 1, there's an associated number called the Ricci curvature of the manifold in that direction. And instead of looking at the volumes of a small ball, you instead look at the volume of a narrow cone. So take a little cone in the tangent space, spray it out by this exponential map, and you could say, and you truncate the cone at distance epsilon away. So how does the volume of the cone in the manifold compare with the Euclidean answer? And there's, in the same spirit as before, if you take the volume of this cone, you assume that the spherical angle that it subtends is very small, and now for fixed spherical angle, just consider how its volume depends upon the radius epsilon. And so the volume in the manifold versus what you would expect in Euclidean space, again, to lowest order it's just 1, and then there's a quadratic correction, and then the coefficient here is called the Ricci curvature. So this is, again, there's a little fudge factor because the Ricci curvature, the scalar curvature, they were not invented this way. They were invented by a fairly algebraic process without really thinking what was the geometry that these things recorded. They both were invented by Ricci, one of the great Italian Riemannian geometers from early in the 20th century. Okay, so a manifold is, a Riemannian manifold, or a metric, is said to be Ricci flat if its Ricci curvature vanishes identically. And of course, this is still a much weaker condition than being flat. So there's another kind of curvature, which I didn't put on the slides, called sectional curvature. So this Ricci curvature assigns a number to every unit vector, or every direction in the manifold. But there's also a notion of sectional curvature, which given a two-plane in the tangent space, gives you a number. And that number actually is simply, you take this plane, spray it out into the manifold using the exponential map, you get a surface. That surface has an intrinsic geometry induced. At a point, it has a scalar curvature. That's the scalar curvature of a surface is, in dimension 2, is almost the same as what Gauss invented. The Gauss curvature is actually only half the scalar curvature of a surface. All right, so you could say, what's the curvature not of the entire n-dimensional manifold, but just of that two-dimensional surface that you got from taking a plane in the tangent space and following geodesics. That's called the sectional curvature. Sectional curvature contains a lot more information. If all the sectional curvatures are 0, that happens if and only if the manifold, if they vanish for every plane in a certain neighborhood, that neighborhood is actually isometric to a piece of Euclidean space. So it encodes the entire Riemann curvature tensor. All right, so here's a simple natural problem. Here's the beginning of the real lecture. So here's a simple natural problem. Suppose you have a complete non-compact Riemannian n-manifold. So complete means that you could say it's metric space complete, or every geodesic runs forever, can be extended as a map of the real line. Those are equivalent conditions. So if you have a complete non-compact Riemannian n-manifold, here's an example. So you might imagine the following situation. Suppose there was a compact set, and outside the compact set, what was left over just looked like the complement of a ball in Euclidean space. And let's assume for the moment that actually the complement of this region is actually dead on isometric to Euclidean space. So we have some metric here which just looks like the Euclidean metric, and then here we've changed it in the middle, maybe changed the topology and so Now you could ask, does this imply that the manifold is flat? Well, certainly not. You could just, I've drawn a picture that would show you how you can get examples. You just take some piece of the plane and then you change the topology and you can change the curvature in the process. It won't be flat. But, so we assume that it's dead on Euclidean outside of this compact set. If you assume that the curvature of this entire manifold is non-negative, the question is this flat? And now the question is, what kind of curvature are we talking about? It could be, if you were to say this for sectional curvature, it's relatively easy to prove that this is true. So you can do this by using distance comparison arguments. Another thing you could ask is, suppose you just knew that the Ricci curvature was non-negative. So I talked about Ricci curvature. There's a notion of Ricci curvature in every direction. If that's non-negative, is the manifold flat? And there are some very elegant, simple proofs of the fact that this is true. For example, if you know about the Bishop-Gromov volume comparison, you would easily prove that the manifold would have to be flat. But what if we just know that the scalar curvature is non-negative? I've told you that the scalar curvature doesn't control the geometry very well. With something like positive Ricci curvature, you can actually prove that there are natural inequalities. If you have a manifold of non-negative Ricci curvature, and you look at a very large ball, even if it's of radius 1 million, then it'll turn out that its volume has to be less than the volume of the ball in corresponding ball in Euclidean space, with equality only if it's flat. But scalar curvature, there's no such volume comparison you can get from a scalar curvature inequality. Nonetheless, the answer here is yes. Sorry.
Sorry, can I just ask? So it's the first time I'm seeing this. Is there a condition on the regularity of the metric for these?
I'm perfectly willing for you to assume that the metric is C infinity right now, but this actually will depend on very little regularity. It's certainly all of these statements are true if the manifold, if the metric is merely C2.
Okay, but the curvature has to be.
So the curvature is not defined if you don't have if you have less than 2 derivatives of the metric, then you couldn't define what you mean by curvature.
I feel like you can imagine a counterexample of course, if the curvature is not continuous, right?
Yeah. So if it's you assume that the metric is at least C2, then that tells you the curvature is continuous. Right? But for simplicity, just assume that everything's C infinity. The proofs all do work with minimal regularity. All right. So if this is actually a true statement, if the manifold has scalar curvature greater than or equal to 0, and it dead on looks exactly like Euclidean space outside some compact set, then this weak condition, the scalar curvature is greater than or equal to 0, is enough to guarantee it's actually Euclidean space. At least, if you assume the manifold is a spin manifold, or if its dimension is less than 8, there's now an announcement of Shane and Yao believe that they have a proof of this in general dimensions. I'm going to tell you a different set of results, though. This involves ideas that originally came from physics, specifically gravitational physics. The important thing, so this would be kind of a very specialized problem if you were only talking about metrics that were actually equal to the Euclidean metric outside some compact set. But in fact, you don't need this. This works with a much weaker hypothesis. You simply need that the metric falls off to the Euclidean metric at a sufficiently fast rate as the radius gets large. So here's the kind of class of manifolds where one works with in this context. One says that a complete non-compact Riemannian manifold, and here now this is going to become a fake picture. I'm always going to assume that the real dimension of the manifold is at least 3 for this definition. In dimension 2, there's not really going to be much going on anyway. So from now on, we have a nice 2-dimensional picture to look at, but you're supposed to imagine the manifold's at least dimension 3. So it's a complete non-compact Riemannian n-manifold is said to be asymptotically Euclidean, or just, that's abbreviated as AE. If there's a compact set and a diffeomorphism from the complement of the compact set to Euclidean space minus a closed ball, such that when you transfer this metric over onto Euclidean space, it looks like its components are those of the Euclidean metric, plus terms that fall off like 1 over radius to the n over, or a little bit faster than 1 over radius to the dimension over 2 minus 1. And you assume also that the first derivatives, for all the first partial derivatives of metric components, fall off at the rate that you would then expect. When you take the first derivative of a power of r, okay? Power of the radius. And then the last condition that one puts on is I want to assume that the scalar curvature is an L1 function. So the absolute value of the scalar curvature is L1. So in my notations, red S is the scalar curvature. All right, so that's this class of manifolds that are called asymptotic Euclidean. Now, actually, one can weaken this condition. Rather than assuming that the complement of some compact set is one copy of Euclidean space with a slightly perturbed metric, you could assume that the complement of a compact set was a disjoint union of sets that were diffeomorphic to the complement of a ball in Euclidean space. And such that, so on each of them you have a diffeomorphism in such a way that the metric looks like the Euclidean metric plus terms that fall off fast at infinity. All right, so here I've made an assumption about the value of the metric, but also its first derivative, and then the scalar curvature involves two derivatives of the metric. But here we've just assumed that the scalar curvature has absolute value an integral function. All right, so this is the class of manifolds called asymptotically Euclidean manifolds, or AE manifolds. And here, in general, you could have several different ends. So the different connected components of the complement of a compact set would, in this context, would be called the ends. All right, so physicists thought about this in the specific case when the manifold is a Riemannian manifold of dimension 3. And in relativity, space-time is a 4-dimensional pseudo-Riemannian manifold, so it has, the metric would not be positive definite, it would have 3 positive directions and 1 negative direction in representing time. But you can talk about an initial data surface, or a space-like slice, and it would have an induced Riemannian metric. So in that context, one could assume that the induced metric had this kind of behavior. It looks pretty much like the Euclidean metric at infinity, but with some slight perturbation. When you're looking at an isolated gravitational system, and a typical thing you could think of is like a star or a black hole that's sitting alone in the universe, and the rest of the universe is empty, you would imagine that it looks pretty much like Euclidean space at infinity, and then you'd be in this situation. So in that situation, physicists came up with a definition of what they would call the effective mass of the system. It's a certain real number. And the algorithm is that this is a horrible coordinate kind of definition. It's very hard to see the geometry. You start off by taking the divergence of the metric minus the gradient of its trace with respect to, so here, this is written in the Euclidean, you're thinking of, you have a standard chart at infinity, so you're using kind of Euclidean coordinates. Then you take the radial component of that with respect to the outward pointing unit normal and integrate that on a very large sphere. Take the limit as the radius of the sphere goes to infinity, and then there's some normalization factor which is conventional. Depends on the dimension and so forth. So here we're integrating on a very large sphere, the sphere of radius rho in Euclidean space, just in that chart. And here the nu is the outward pointed unit normal with respect to the Euclidean metric, and we're now getting this large sphere, the induced area form from Euclidean space. And so obviously, I mean, this looks like it depends on the choice of coordinates. It doesn't seem to be geometric at all. It's not built out of the metric, it's built out of this coordinate system. However, independently, Robert Bartnik and Piotr Krushil proved in 1986 that with the kind of weak fall-off conditions that I've imposed, that actually this notion of mass is independent of the choice of coordinates.
And so is the sphere, you can center the sphere anywhere in this definition?
Well, so here, yeah, it turns out that it is invariant under, yeah, it's just the main thing is that you have a diffeomorphism to the complement of a ball, so you would normally center it at that point. But if you were to shift over by a shift where the region that you're missing was still within the ball, and then take the radius to be bigger and bigger, yeah, you'd get the same amount. And that's an example of this kind of coordinate invariance.
Just sort of a dumb question. I mean, how do you measure the distance because there's something missing in the middle?
Absolutely. So like I said, this is all set up by saying you start off with a particular diffeomorphism of complement of compact set to Euclidean space minus a ball. And all of the things in this formula are done with respect to the Euclidean coordinates. So it's really doesn't look geometric at all. So what I'm going to show you is that actually in a certain context, it has a more geometric meaning. Okay, so in an appropriate sense, this is coordinate independent. There's a lot of freedom in choosing how you chose this diffeomorphism to Euclidean space, and as long as you kept the same fall off, you'll get the same answer.
So is it a positive? What is it a positive finite real number?
So the mass a priori, right now in this context, all you know is that it's a real number. It is finite.
Okay.
That fall off is enough to guarantee the number is finite, but it's not obvious. Whether it's positive or negative or zero is going to be an issue that I'll be discussing. So the motivation is that when you're talking about this in the context of three manifolds, this expression specializes to become what's called the ADM mass, where this is Arnowitz, Desner, Misner, the people that invented it. It reads off. They sort of did this. It was generalizing different examples and just looking at well, what kind of expression could you write down. It's the apparent mass from the strength of the gravitational field from an isolated source. So the sort of thing you're supposed to think about is you've got in general relativity, the gravitational field is represented by the metric. That's why the metric is called G. It's Einstein. G actually meant gravitational field for Einstein. And far away there would be some pretty commonsensical notion. Einstein's gravitational theory starts looking very much like Newton's when the field is weak, and you could say, what's the effective? If you just throw a stone and see how it moves in this gravitational field, what is the apparent strength of the gravitational field? What is the mass of that source? Now, in Newton's theory of gravitation, you can find out the total mass of a system just by integrating the local masses. But general relativity is a nonlinear theory. The equations are nonlinear PDEs, and when you superpose different sources of matter, well, it turns out that there's a sort of self-gravitational, that empty space can have a sort of feedback where it generates its own gravitational field in many solutions. So even though you might have no local mass in a black hole solution, it looks like it's empty space, and nonetheless, it acts like there's a missing star there. All right, so this is asking questions about, so in particular, if this is supposed to be the mass, under physically reasonable circumstances, you'd expect that this mass should be positive and not negative. In Newton's theory, the mass of realistic matter is always positive. And so that's one of the issues that we'll be talking about. So here's a typical example that motivated this definition by Arnowitz, Desner, and Misner. They were always interested in the case of n equals 3, so the space-time dimension before. And then there's a famous Ricci flat metric. This is the exterior Schwarzschild metric. So so you notice there's one negative direction, and this would be three positive directions, or if you're in dimension n, this would be n positive directions. Here, this rho can be thought of as a radius coordinate. It's really tied to this. Here we have a standard metric on the n-1 sphere multiplied by radius squared, and so there's an effective radius built into this definition, which is not actually the radius in the sense of measuring the length of something. It has to do with the areas of certain large spheres defined by the symmetry group. All right, so if you cut out the time direction, this is what the metric looks like. It's not, but it depends on a certain quantity m, which is called the mass, the Schwarzschild mass. So this is in n equals 3. This is a good model for the exterior gravitational field of a star that's not rotating too fast. So I've described this. Right now, this is not a complete metric, but actually, if you take, so this is only defined when the radius is large with respect to this mass. So when rho over n-2 is bigger than 2n. But actually, if you take two of these regions, right now this is defined on something that looks like a half line times a sphere, but you could think of that as Euclidean space minus a ball. Actually, if you take two of the regions where this is positive definite and glue them together, that forms what's called the wormhole metric, and that's actually, interestingly, you can write it as a conformal rescaling of the Euclidean metric times a certain power of the 1 plus the usual Green's function for the Laplacian on Rn. This is related to an interesting role of the Laplacian in the Yamabe problem that you're asking about. So this is, right now, this is defined on, if you write it in this way, it's defined on Euclidean space minus the origin, but there's a conformal inversion, which actually is an isometry of this metric. This is scalar flat, asymptotically Euclidean, and it has, this case has two ends. And the mass that you get at, so this is, keep in mind, this Riemannian manifold is not Ricci flat. The space-time that it came from was Ricci flat, but when you just restrict to the spatial hypersurface, it's only the scalar curvature that vanishes. In this particular case, the mass is the same at both ends, but that's not true in all possible examples of the mass. When you have several ends, you could have different masses at different ends. If you have several ends. In this case, though, you could think of this mass as basically measuring the size of this Schwarzschild throat, the size of the wormhole. So if in this particular case, if you were to just forget about the higher order terms, the metric basically looks like the Euclidean metric times 1 plus a certain multiple of 1 over the radius to the n-2. This is so this is Green's function type of factor. And the crudest definition, in fact, most of the early mathematical papers that dealt with mass did not take that complicated integral formula. They just assumed the metric looked like this plus lower order terms. And so when Shane and Yao first worked on the positive mass theorem, they assumed the metric had this form, and then it was extra work to get this to not make, so the fall off that I assume is actually much weaker than this. So it's only, rather than assuming that you have a deviation that looks like the radius to the n-2, I allow something, a power of r that's half of this. It's not me, it's people that figured out that were really Crucial, I think, was the person who really first emphasized that this much weaker fall-off was good enough to define the mass. All right, so we've been talking about asymptotically Euclidean manifolds, but here's an important and interesting generalization called asymptotically locally Euclidean manifolds. And these are called ALE spaces because, of course, they were discovered over pints of beer in a pub. The variation on the definition is that, again, we assume that there's a compact set such that the complement is nice, and the change is that each end is no longer required to be a copy of Euclidean space minus a ball, but instead each end is a copy of Euclidean space minus a ball modulo the action of a finite group of isometries that acts freely on the sphere. Has to act freely on the sphere, otherwise you wouldn't get a manifold into the quotient. All right, so we have a finite group of fixing the origin in Euclidean space and acting freely on the unit sphere, preserving the Euclidean metric, and then we have diffeomorphisms from each end to that kind of model with exactly the same fall off as before. So if you like, here actually these groups that are acting, because I'm in dimension 3 or higher, these are simply the fundamental groups of the ends. And it's really saying that the universal cover of each end looks like Euclidean space minus a ball with some perturbed metric. Well, why would you consider ALE spaces? Well, the reason for doing anything in mathematics is that there are examples. The key examples were discovered by Gibbons and Hawking in 1979, and that was when they invented this terminology ALE, asymptotically Euclidean. What they wrote down were Ricci flat ALE manifolds called gravitational instantons. Now, if you have a Ricci flat asymptotically Euclidean manifold, you can prove that it is necessarily flat. But if you weaken the asymptotic topology and allow it to look like a quotient of Euclidean space, then you can have non-trivial solutions. So their examples have just one end, and in fact that's related to the fact that they're Ricci flat. The so-called splitting theorem of Cheever and Gromall would always tell you that in the Ricci flat case, you can only have one end. So in their examples, the fundamental group of the end is just a cyclic group, and it's not. You think of this as sitting in SU2. So we have generators like this, where zeta is a root of unity, and so these metrics are Ricci flat for an extremely interesting reason. They're so-called hyper-Kaehler metrics. And Hitchin then rediscovered these metrics by a completely different way. What's a hyper-Kaehler metric? Well, first of all, I have to say what a Kaehler metric is, if you don't know. This is a natural notion in Riemannian geometry, and it's related to the notion of holonomy group. If you have a Riemannian manifold and you choose a base point and then consider some arbitrary loop, piecewise smooth loop, starting and ending at that base point, you can drag tangent vectors around the loop to define a linear transformation from the tangent space at the base point to itself. That's called a holonomy transformation, and you get a different holonomy transformation for every loop. So it turns out that the set of all holonomy transformations, in this case, because the metric preserves the metric is preserved by the connection, this holonomy group is automatically in the orthogonal group. The point is that it is a subgroup of the, when you take all possible loops, you actually get a subgroup of the orthogonal group in this way. The way that it sits in the orthogonal group, strictly speaking, depends on the choice of an orthonormal basis, but up to conjugation, it's a well-defined subgroup of the orthogonal group. A metric from this point of view is Kaehler, if and only if its holonomy consists of unitary transformations. In other words, orthogonal transformations that are also complex linear. Obviously, this only makes sense if the real dimension is even, and we're saying that there's some choice, relative to some choice of orthonormal basis, this homonymy group is actually a subgroup of the unitary group, or if you like, up to conjugation, it's a unitary group. This means that all of these homonymy transformations actually preserve a complex structure on the tangent space. The tangent space at the base point is actually a complex vector space, and moreover, that's true in such a way that it's invariant under parallel transport. So in particular, you can make every tangent space of the manifold into a complex vector space in a consistent way. That would be saying that it automatically is associated with an almost complex structure on the manifold. But in fact, this is automatically an integrable complex structure. The fact that J is preserved by a torsion-free connection implies that this satisfies the vanishing of the Nienhaus tensor. This is actually an integrable complex structure. So in fact, the usual way of defining a Kaehler manifold, Kaehler didn't know about this, that it had anything to do with homonymy. He just wrote down some weird class of metrics, which I'll describe. But in fact, these metrics always live on, you can always think of the manifold as a complex manifold. From the Riemannian point of view, it's a Riemannian manifold that has a special property of its homonymy. But in fact, that makes the manifold into a complex manifold in such a way that the almost complex structure is parallel, and such that such that the metric, such that the complex structure actually preserves the metric. So if you multiply a vector by I, as it were, it doesn't change its length. The usual way that you'll see this described in most textbooks on, say, transcendental techniques in algebraic geometry, or it would instead say you have a complex manifold and you have a metric that's expressible in terms of a closed two form. And it's a very interesting set of lemmas that this is in fact the same thing as this homonymy definition. So there's an associated two form that you get there's a unique two form which has the property that if you stick J into one slot, you get the metric. That's called the Kaehler form. And it's automatically a closed form, so in particular it has a de Rham class called the Kaehler class. So there's a preferred element of the second de Rham cohomology on a Kaehler manifold. The way that what Kaehler actually did was he said, let's look at the following weird class of Riemannian metrics. Take a function, take its second derivatives with respect to the complex coordinates, only consider things with one z derivative and one z bar derivative. So it's like taking the Hessian of a function, but it's actually only a piece of the Hessian, looking at these mixed partial derivatives. And out of that, suppose that this is actually positive definite. So that was actually what Kaehler did. Kaehler discovered something that's deep, though, that so the Kaehler form here is written down in terms of, again, the second derivatives of the function. And what Kaehler discovered was that the Ricci tensor of such a thing, again, is expressible in terms of second partial derivatives of some potential function. It's not the same function. You take the log of the determinant of the original metric. And that reflects a deep geometric fact. The Ricci curvature of these manifolds actually is encoded in the so-called Ricci form. So you stick a J into the Ricci tensor, you get a form called the Ricci form. It's a closed two form, but actually it's the curvature of a certain line bundle, of the canonical line bundle. All right, so those are Kaehler metrics. But if you look at those where the homonymy is not just in the unitary group, but it's in the special unitary group, that would exactly say the canonical line bundle is flat, and therefore the Ricci tensor is zero. So homonymy in SUM implies the Kaehler metric is actually Ricci flat, and in fact, if you assume the manifold is simply connected, these are the same thing. So so here the special unitary group consists of unitary transformations which have complex determinant 1. So for a manifold that's simply connected, saying being Ricci flat Kaehler is exactly the same as saying its holonomy is contained in the special unitary group. Hyperkähler metrics are those where the holonomy is instead contained in the symplectic or the quaternionic group. So SPL is by definition the intersection of the orthogonal transformations in O4L with, so those transformations which are also quaternionic linear, thinking of these as transformations of quaternions to the power L, HL is R4L. And this group, which was first given a name by Hermann Weyl, plays an essential role in the classification of compact groups. One of the basic elements. So this is actually a subgroup of the special unitary group, and so any manifold with this holonomy is automatically Ricci flat Kaehler. But in fact, SPL sits in the special unitary group typically in many different ways. In particular, you could just, among the quaternions I, J, and K, you have a choice of which one you think of as the complex number I. And that would give you different ways of thinking of this as sitting in the standard special unitary group. So in fact, a hyperkähler manifold is a Kähler manifold in many different ways. There's actually an entire 2 spheres worth of different complex structures it carries, corresponding to the different quaternions that have square root equal to -1. In dimension, in real dimension 4, actually the group SP1 is just the same as SU2. It's the 3 sphere as a group. It's the unique Lie group diffeomorphic to the 3 sphere. And which you could think of as the unit quaternions with multiplication as the group operation. So when the manifold is simply connected, being a hyperkähler in dimension 4 is actually exactly the same as being Ricci flat Kaehler. The only difference is you have a choice of, actually there's more than one compatible complex structure on a Ricci flat Kaehler manifold on a simply connected 4 manifold. Okay, so since there's an entire 2 sphere of different complex structures here, it's interesting to package these into one object. You could imagine that you have a family of different complex structures, but then they're parameterized by something which you could think of as CP1. When you do that, this is an idea basically due to Roger Penrose reformulated by Atiyah Hitchin and Singer. You get what's called the Penrose twistor space of a hyperkähler manifold. It is a complex 3 manifold, and it has some extra structure. For example, it has a holomorphic map to CP1. So that is one way of dealing with the fact that there's more than one complex structure. And in fact, what Penrose showed was that this complex 3 manifold can actually be used directly to describe the general hyperkähler metric. When Hitchin rediscovered these Gibbons-Hawking metrics, Gibbons-Hawking had just written down, using a certain piece of nice physics yoga, method for constructing such metrics. Hitchin instead used the Penrose twistor space in order to, he found the Penrose twistor spaces and then constructed the metric from that. He also conjectured that if you had any finite subgroup, so in this case, you know, the N has fundamental group, a subgroup of SU2, and Hitchin conjectured that for any finite subgroup of SU2, you would have a corresponding family of hyperkähler metrics. These are also called gravitational instantons. That conjecture was then proved by Peter Kronheimer in his thesis. In fact, the classification, I should speed up a little bit. In fact, the list of things you get, they're all metrics on resolutions of C2 mod gamma, where gamma is a finite subgroup of SU2. And those things, Felix Klein realized that these were C2 minus mod gamma for all finite subgroups of SU2 can be realized as a hypersurface in as a complex hypersurface in C3. and wrote down for each possible thing. The groups that you're talking about, after all, SU2 is the double cover of SO3. These groups are all things that people have known about since the Pythagoreans in ancient times. They're things like you take the group of motions of the icosahedron and then you pass up to the double cover of SO3. So all of these classical geometric objects are actually associated with hyperkähler manifolds. There's also an interesting piece of yoga in trying to understand the topology of these manifolds. It turns out that the generators of their homology in dimension 2 are exactly in one-to-one correspondence with the nodes of a certain Dinkin diagram, and there's a McKay correspondence that goes back and understands how this diagram comes about from the representation theory of this finite group together with its given representation on C2. All right, so the point is that there's a beautiful classification there. We know all of these gravitational instantons now through the work of Conjecture. Now, I said for hyperkähler metrics there was this Penrose twistor space, and this is something that you get when you have a Kähler metric on a four-manifold which is Ricci flat. But in fact, you don't need it to be Ricci flat. It's enough for its scalar curvature to vanish. That's enough to guarantee that there is this integrable three-manifold associated with it called its twistor space. And in my youth, I studied twistor spaces of scalar flat Kähler manifolds and I used these ideas to construct new scalar flat Kähler ALE manifolds. Did many other things too, but this was an interesting aspect of
So wait, this twistor space, I see what the complex structure should be for if M is hyperkähler, because for each complex structure in the sphere you use that.
Yeah.
But
so you can in fact define this twistor space without having a complex structure on the base. The point is that the fiber consists of all possible almost complex structures at each point, which are compatible with the metric and the orientation, which is a two-sphere. And so in this case, there's one cross section. There's an embedding of the complex surface in there. In the hyperkähler case, you get a family of such things. But in general, there's an integrability condition, which is a piece of the curvature tensor, the self-dual-vowel curvature has to vanish. And so there's an integrability, even for Riemannian manifolds that are not Kähler, there's a sensible twistor theory given a certain equation, but it is in fact particular satisfied for scalar flat Kähler manifolds.
So the projection to P1 is still homomorphic?
There is no projection to CP1.
No projection.
So here the picture is different. You have the complex surface that you're working on it sits in the twistor space, as does its conjugate, where you have changed the sign of the almost complex structure. But nonetheless, that's enough information to learn a lot. In particular, I showed that if you took a line bundle over CP1 with negative Chern class, that admits an ALE scalar flat Kähler metric, and also if you blow up that complex surface in generic configuration of points, you again get scalar flat Kähler metrics on it. All right. So these spaces have turned out to arise very naturally in a lot of problems in the Riemannian geometry of compact manifolds when you're looking at sequences of Einstein metrics or solutions of a weaker equation called the Bach equation. Then these kinds of metrics arise as bubbling nodes. When you have concentration of curvature, you change the scale, you zoom in and see what's going wrong. It has to do with the formation of one of these kinds of metrics. There are lots more ALE scalar flat Kähler metrics that have been discovered since my work. I mentioned the work of Joyce, Calderbank, and Singer, and of Vyakovsky and Locke. But we don't have a full classification in this general setting. That's still a problem. All right, so finally I should get to the heart of the matter. So if we have an ALE manifold, it still makes sense to talk about its mass at a given end. And the definition is almost exactly the same. The only difference is that here, by convention, I'm taking this integral to be, so in the end, you think of the end as it's a cone over a space form, and you're taking the quotient, the integral here is not over a sphere, but over a quotient of the sphere. And that's a conventional thing, you could debate of whether you should take the integral in the quotient or upstairs, that it would introduce a certain factor. It turns out that doing it this way is better. Otherwise, same definition as before, and the same theorem of Bartnik and Crucial applies. So there is a coordinate invariance of this mass, and it's a well-defined finite number. On the other hand, if we were to say, well, if we looked at the gravitational instantons, those turn out to always have mass 0. This is related to the fact that they're Ricci flat. Bartnik had shown that for Ricci flat, the Ricci flat condition makes the metric fall off faster at infinity, and the terms that contribute to the mass are trivial. But if we're looking at scalar flat Kaehler ALEs, then the mass is typically non-zero. Here's a nice simple example of a scalar flat Kaehler ALE manifold. In fact, this is AE, it's asymptotically Euclidean. This example was pointed out by Dan Burns to me at a conference, therefore we call it the Burns metric. And it actually was the inspiration for all the constructions that I did after that. So consider the blowup of the origin in C2. That's a fancy way of saying, look at the total space of the tautological line bundle over CP1. The tautological line bundle over CP1 replaces a point in C2 with, so you replace the origin in C2 with all of the possible complex directions. So away from the origin, it's just C2, but you've stuck in a CP1 at the origin. This process is called blowing up. The total space here is actually, there's an extra CP1 direction which measures the direction of the line. So this is actually a line bundle over CP1. It's the one of Chern class -1. Now on this, you can look at the following very simple metric. Just say, well, this is contained in Euclidean space times a 2-sphere. CP1's a 2-sphere, and you give it the standard round metric. Now take that, so this is now a subset there, and the following strange miracle happens. The induced metric is not just Kaehler, it has scalar curvature 0. And this doesn't happen for any reason other than you do the computation. The scalar curvature is 0. You can write this down. If you want to identify this away from the origin with C2, this would be, the Kaehler form is I over 2 dd bar of u plus 3m log u, where u is the radius squared. And here, this number m, which comes from the size of the 2-sphere, and it's just the size of the 2-sphere, is this mass, and it's automatically positive. All right, so if you we've said that you can talk about the mass of an asymptotically local Euclidean manifold at a given end. In particular, you can talk about mass in the asymptotic Euclidean setting. So the positive mass conjecture is that an asymptotically Euclidean manifold with scalar curvature greater than or equal to 0 has mass greater than or equal to 0. And the intuition there is from physics. The scalar curvature in this context corresponds to the local mass density of non-gravitational sources of the stuff other than gravitation in the system. And if the local matter density is greater than or equal to 0, you would hope that the effective gravitational pull of the system is always positive. The mass should be positive. This was proved initially in dimension 3 by Shane and Yao, and their proof can be generalized to up through dimension 7. It uses minimal hypersurfaces, and it starts breaking down in high dimensions because minimal hypersurfaces don't have to be smooth in high dimensions. Witten gave a completely different proof in 3 dimensions, but it actually, using the Dirac operator, and it actually works for a spin manifold of any dimension. Hawking and Pope, around this the same time as the work of Shane and Yao, the papers published beforehand, but that's because physics papers are published very quickly, They don't have to be correct, they just have to be interesting. They conjectured in their paper that this positive mass property would also be true in the ALE case. I discovered that this is actually false. So there are counterexamples. In fact, among scalar flat Kaehler metrics, if you take a line bundle of Chern class -3 or more negative than that, and you look at one of these metrics I mentioned before, it turns out it has negative mass. Actually, when I first wrote down these metrics and submitted the paper for publication, I thought they were just so interesting. Obviously, the paper would be accepted by this journal, and it was rejected, saying, I don't see what this is good for. And then my colleague, Mike Anderson, said, well, why don't you calculate the mass? You know about this paper by Hawking and Pope? So I calculated it was negative. So I sent it back to the same journal, they immediately published it. And so, if for young people, you should know this story, right? Just when you're young and unknown, people will just find an excuse to reject your paper. Just get somebody with more experience to tell you how to tweak it, so that it'll be considered. Anyway, I'm glad that I calculated the mass. It went somewhere. So the basic question is, what can we say about the mass of ALE Kaehler manifolds? And in particular, I said I'm interested in the scalar flat Kaehler case, initially in complex dimension 2, real dimension 4, but you could ask this in any dimension. Well, one little lemma is that an ALE Kaehler manifold only has one end. So when you're trying to talk about its mass, it's an invariant in the manifold because there's only one end there. In general, you could have many ends and they could have different masses. But here, in this Kaehler setting, there can only be one end, and so there's a mass that's an invariant of the manifold. So the mass of an ALE Kaehler manifold is an unambiguous invariant of the manifold. And in the scalar flat Kaehler case, the main theorem is the following. The mass of an ALE scalar flat Kaehler manifold is actually a topological invariant. It's completely determined by the smooth manifold, by the first Chern class in the second cohomology, and by the Kaehler class in the second cohomology. In fact, the underlying fact is, this is an abstract statement that it's an invariant, but in fact, there's a formula. And I'll show you the formula in a moment. So before, when I calculated the mass in that example, I just did it by brute force. It turns out, if I'd known what I was doing, I could have seen that it was just some nice topological thing. So actually, when you get this formula, there are other applications. For example, if you have an ALE, so the negativity I noticed was actually a symptom of something much more general. Suppose you have an ALE scalar flat Kaehler surface, and suppose it's a minimal resolution of a surface singularity. This only applies in the minimal case, it's not the blow-up of something else. Then the mass is never positive in this case. And you get 0 only if it's Ricci flat. By the way, this fails. Once you start blowing up, you can change the sign of the mass. It can go from being negative to positive. All right, so here, let me tell you about the explicit formula before I wind up the lecture. So the explicit formula depends upon a topological fact. In this setting, if you have an ALE manifold of real dimension at least 4, then the natural map from the compactly supported cohomology to the Durand cohomology is an isomorphism. So compactly supported Durand cohomology means that you look at the complex of compactly supported forms rather than all smooth forms. And this actually is essentially looking at the relative cohomology of the manifold modulo infinity. So, here this is defined. But the point is, for these classes of manifolds, it doesn't matter whether you use compactly supported forms or non-compactly supported forms. The cohomology in dimension 2 is the same. And so, in particular, it makes sense to introduce some kind of notation for the inverse of this map. We denote it by Claude as a map from H2 to H2 compactly supported. That's what you do is you take, given a closed form, you club it over the head until it's compactly supported, and then you take its, compactly supported Durand class. All right, so
that sounds like a proof.
Well, that idea actually sort of comes into the algorithm. The proof involves coming up with specific representatives. All right, so here's the mass formula. So if you have an ALE Kaehler manifold of complex dimension m, so m in blue is the dimension, and m in black will be the mass. That's also in a different font. Okay, the mass of the manifold it has a contribution that's coming from the integral of the scalar curvature. You wouldn't see that if it was scalar flat, times a certain coefficient that depends on the dimension. And then there's a contribution which you take the club of C1. So this is now something you compare with a second. This is compactly supported, so you can now pair it with something in H2m minus 2. So you take the Kaehler form cup itself m minus 1 times, pair it with club of C1, and then multiply by an appropriate thing. So here's a closed formula for the mass, and in particular you see that if the scalar curvature is 0, you wouldn't see that last term, so you get something which is just a topological invariant involving C1 and the Kaehler class. So here, remember, the integral of the scalar curvature is actually against the metric volume form, so this is really a nice geometric thing, unlike the definition of the mass, which involved using Euclidean space. So the contributions in this case in this formula are all very natural things, natural topological things, natural geometric things. This is a mysterious looking formula, but it's related to a fact about compact complex manifolds. So if you have a compact complex manifold, the integral of the scalar curvature is actually something you can read off by pairing C1 with a power of the Kaehler class. And so you would get that a certain combination of the integral of the scalar curvature with minus a multiple of C1 cup omega to the m minus 1 was 0. So this formula reflects the fact that the scalar curvature is the trace of the Ricci tensor, and there's a way of computing that by taking the Ricci form wedge a power of the Kaehler form. All right, so so if you look at the formula that I just described, it actually says that the mass is an anomaly that measures the degree to which this formula fails. So that was a formula in the compact case. In this non-compact case, the formula doesn't quite work. And so the degree that it fails is actually measured by the mass. Okay, so it's a boundary correction to the topological formula for the scalar curvature. All right, so so we actually find that one consequence of this formula is this formula for the mass. I don't have time. I spent time talking about more elementary issues, so I'm not going to try to tell you about the proof. But I will just point out a couple of other results at the very end. Sorry to close your eyes if this bothers you. In fact, one consequence is that this formula gives a simple proof of the positive mass theorem in the Kaehler case. So if you have asymptotically Euclidean, not asymptotically locally Euclidean, but asymptotically Euclidean and Kaehler with non-negative scalar curvature, then the mass is greater than or equal to 0. But in fact, the proof shows a lot more. So, by the way, the positive mass theorem would tell you that also if the mass is 0, then the manifold must be Euclidean space. Actually, our proof shows more than this because it actually gives an effective lower bound so that's an analog of the Penrose inequality in relativity. In fact, if you have an asymptotically Euclidean Kaehler manifold with scalar curvature greater than or equal to 0, what you can show is that the underlying complex manifold is actually has a nice holomorphic map onto Cm, which is bihomomorphism away from some compact set. And so in particular, there's a canonical divisor, which is a sum of compact complex hypersurfaces with integer coefficients, which represents the canonical class. And you can use that to then say that actually the mass is bigger than the sum of the volumes of those hypersurfaces with appropriate weights, and that you get equality exactly in the scalar flat Kaehler case. And the only case in which this divisor is trivial is if the manifold is CM. In that case, you can then prove that the manifold is actually Euclidean space. All right, so I've covered a lot of material today. I hope it's been useful. I'll stop now.
Are there any questions?
Did you say that these D's are, if you add the D's are a compactification of M? You know,
So a priori, given an ALE Kaehler manifold, does the manifold look like complex Euclidean space outside a compact set? We've said it looks diffeomorphically like real Euclidean space, but it's the complex structure standard. It turns out, well, in complex dimension 2, that's false in general. In higher complex dimensions, it's always true, but in any dimension, if it's asymptotically Euclidean, the manifold actually not only looks like complex Euclidean space outside some ball, but there's always a holomorphic map. What you can do is you can compactify it by adding a hypersurface at infinity, which looks like projective space. You get a nice linear system that maps it to projective space. And you cut out the divisors, you've constructed a map to CM, which is a biholomorphism, except that it collapses some compact set. So the manifold is actually some modification of CM. And that goes into this, because then on CM you have the differential dz1 up to wedge dzm. You pull that back, it cuts out some hypersurface. That's this divisor. So if the canonical if this divisor is trivial, the manifold must actually be biholomorphic to CM, and then it's not very hard when you have a scalar flat Kaehler metric, which is on CM, that the first Chern class vanishes. You end up reading back it has to be Ricci flat, because the Ricci form for scalar flat Kaehler manifold is harmonic. And then you can just use Bishop-Gromov inequality and say, it's actually it's Euclidean space. So the arguments here are sort of very simple. They're sort of very simple and very clean compared to
this reminds me of, I don't know, it seems related to Mach's work on compactifying complete. So like Mach writes down the same mass that you wrote down, except that he doesn't use the Ricci as a representative of the cohomology class. He doesn't take the scalar curvature or the Ricci curvature, but he takes a divisor. So dd bar log of a section or something, and he writes down the same exact thing, which is 0 on a compact manifold, just as you did. But in his case, it's a much simpler thing. In his case, it's always positive. His mass, which uses a different representative, is always positive.
Gosh,
but he uses that. He uses it to kind of do the opposite. He uses it to compactify. His theorem is that you can always compactify a complete Riemannian manifold, a complete Kaehler manifold with negatively pinched Ricci curvature.
I'll have to look at this paper.
But yeah, it really reminds me.
Where is that in roughly when?
It's old, in the 80s, and it's probably, I think it's in the Annals. He's written several papers, and also his student, Psyche. But it really, it's very reminiscent.
It's a little different. Mach's case is the boundary. Here, the divisor is the center. You blow up the center.
No, but he said you can compactify it by adding.
This is already Pn. At infinity is Euclidean, just Pn. So the interesting happens in the middle, right? You blow it up.
Yes, that's right. So you sort of
those divided at the center. Mach's in on the boundary.
But I think there are two things going on. One is there's a divisor at the center, but I think you said there's also a divisor.
Well, so the argument involves the fact. So in order to show that you can get this map to CM, the way you do it is you take a certain compactification of the manifold and show that maps to PM in such a way that the thing that you've added at infinity, which is just a copy of projective space, of one-dimension loss, maps to a hyperplane. So, so the point is, you know, if you can show that you can, so the delicate thing is with these asymptotics, you want to show that if you add a complex projective space at infinity, that actually the complex structure extends across. So you have to show that the complex structure is a priori, it's not, you know, not a priori standard, but it also has a fall off. The fall off of the metric gives you a fall off of almost complex structures. And then you want to show that you can therefore extend it as a smooth. You have to use Newland-Nierenberg with very, you know, very rough form of Newland-Nierenberg due to Taylor and Hill.
So Mach also adds a divisor, but in his case, the result is a projective variety. You know, he gets a projective variety out. Yours aren't. These aren't projective varieties, are they?
Oh yeah. Well, so the thing that you know a priori is that they're definitely Moishes on. It's not clear. No, in fact, I'm sorry. They are always projective. They're always projective. So the point is, you do have. That involves some work. So you have some, you know, you have this Kaehler metric on the interior, but then it doesn't extend across infinity. So there's a little technical argument just to hook up a Kaehler metric on the and I think this was not known before our paper. I guess there were some conjectures there would always be Moishes on. So actually, it was projective. So these compactification. And so it's a little bit trickier in the ALE case because the natural analog of this compactification is an orbifold. It's an orbifold compactification. But still, after modification, then you actually do get a Kaehler. So it's certainly, in particular, an orbifold Kaehler. And that's enough to carry out the Gaussian embedding there. So, yeah, it's
Okay, well, let us thank God again.